Now we are beginning the section on energy balances, which incidentally is more thermodynamics. And energy balances here are going to be one additional piece of information for our degree of freedom analysis, because the thermodynamic laws must be obeyed, and so therefore we can use that information to help us solve for unknowns in our process, including mass balances, masses, because the mass and energy balances must go together. So in this lecture we have two parts. In the first part we are going to consider closed and open systems, the general energy balance equation. And in the second part we will consider the tables of data and the reference state. So you should be able to write a simplified energy balance expression for an open system process and use tables of thermodynamic data for an energy balance calculation. The mechanical energy balance will be coming in a later lecture. So why are energy balances important? So for process design you need to maintain optimum temperatures and pressures. There's also issues of process safety, and we also want to be aware that energy has a cost. You have to pay for it, and so you have to figure that in when you do the cost analysis of a plant. So the purpose of this lecture is we are going to be able to identify the correct energy balance for each process step. We will also learn where to find enthalpy values for carrying out energy balances, and we're going to practice solving energy balances. So an energy balance is a statement of the first law of thermodynamics. Okay, so this is essentially the energy change of a system is equal to the heat or work crossing a system boundary. And so that's what we're going to use for our energy balance. So let's take a look at, we have closed systems and we have open systems. However, even in a closed system, which is where no mass enters or leaves the system, we can still have energy entering or leaving the closed system. Okay, an example of such a system is the piston. And this is a part of every engine. You probably participated in a piston coming to school today, unless you walked or rode your bike. When you add energy in the form of heat or work into the energy of the molecules of the system increases. So that is called internal energy, the energy that is in the molecules that are in the system. And we write our energy balance as the change in internal energy plus the change in kinetic energy plus the change in potential energy is equal to Q minus W. And this would be the heat added to the system, and this will be the work done by the system. And we'll talk about that in a minute. Okay, so this is in your book. Okay, we have this Q minus W. And this is going to be different next spring in the thermodynamics class. You will have Q plus W, which actually, in my opinion, is a more reasonable thing. But the reason why they used to have Q minus W is because you generally are getting, most mechanical systems are for getting work out. And so they've assigned work done by the system as positive. Okay, we'll talk more about that in another. So we've already gone through this already, and you've seen this in physics. So you have internal energy, then you have kinetic energy, which increases if the velocity of the system increases. And we have potential energy, which is that it's change in the elevation of the system. Okay, and we write that one as mg delta z, and g here is the gravitational constant. Okay, so heat is going to be in joules, and work is also going to be in joules. All right. So this, on the left-hand side of the equation, notice that these have deltas, okay, and on the right side of the equation they don't have deltas, okay, because Q and W, we refer to a finite amount of energy in the form of heat or work that crosses the system boundary. And whereas the energy side of the equation, these are state variables, okay, and that means that when there's a change, we will identify the delta U as U2 minus U1, the change in the state of the system. And the same goes for kinetic and potential energy, but not with work and heat. These are simply finite amounts of energy that cross the system boundary. All right, so when we talk about work, okay, when we have a closed system, work with the closed system is going to be expansion work, and the piston is the exact case, okay? So if we increase the pressure if we push down on the piston, we're doing work on the system, okay? This here is work done on the system, okay? So if the work is done on the system, then the sign of the work is negative, okay? So work is negative. All right, and now notice that we have work is the integral of P dV, and in this case, when we do this step where we do the work on the system, the volume here changes. It's going to be negative, right? The final volume, V2 minus V1, is a negative number, but work then is also negative, okay? So that means that we end up with this relationship. So W is equal to the integral of P dV. Both of these are going to have negative signs, and that's how we have the integral is positive. Okay. All right. For an open system, okay, when we have mass entering and leaving a system, okay, we've got an m dot in and an m dot out. Here we have only one stream in and out. So if there is to be no accumulation of mass in the system, then m dot in is equal to m dot out, if that's going to be a steady system. So there is a work associated with open systems where you have mass entering and leaving the system that is called flow work. It's the work associated with moving an element of fluid into and out of the system. Okay, so flow work is written as P out V out minus P in V in, or also known as dPV. Okay, but we also have in our system, we have the internal energy. Okay, so there's also going to be a U2 minus U1. So instead of having to incorporate both of these types of work separately, it has been combined into enthalpy. All right, so whenever we do an open system energy balance, we will use enthalpy. Okay, I hope you remember that. All right, and now the work that we still include in this is not going to be flow work. This is going to be shaft work, which means there's a shaft, such as in a turbine or a compressor or a mixer or a pump. Okay, our energy balance looks the same. Okay, we simply count enthalpy now instead of internal energy, and you can find the enthalpy and the internal energy, or we can calculate it similarly. So we're going to work through that as we proceed in our energy balance calculations. Okay, so what is shaft work? Shaft work for a system can be calculated from the integral of minus V dP. Okay, again, the situation is that the work is done by the system, and then it is positive. Okay, so if the work is done by the system, then we find that the pressure change is negative. Okay, but however, the work is going to be positive. Okay, so you'll will see how this comes out as we do our calculations. In our processes, the shaft, okay, we either consider in our class turbine, compressor, or pump. There is also the case of a mixer, okay, and a mixer just beats the fluid, and in fact, a mixer is associated with a motor that does the stirring. Okay, so however much energy of the mixer we have, okay, if you neglect what dissipates by heat, assuming that all the energy in the mixer goes into stirring the fluid, then you can use that as your energy calculation, as your shaft work, WS. Okay, so again, in the pump, the shaft does work on the system. All right, if the work is done on the system, it'll have a negative value. If the work is done by the system, then the work will have a positive sign. All right, so let's do an example calculation. So we're going to use an open system, and what we want to look at here is, and what I want to try to prove to you with this calculation is that the enthalpy change is, if there's any delta T in the system, will be much more significant than the kinetic and potential changes that you could have. So for most of our calculations, we are going to be neglecting these terms. All right, so the idea here is that if you have a delta T, you can probably neglect kinetic and potential energy. And let's prove that by doing a simple calculation. All right, so if the system okay, I've already said that the kinetic and potential energy can be negligible compared to the delta H term. So here's our example calculation. We're going to compare the delta H associated with a temperature change with an equivalent energy change associated with a difference in height or difference in velocity. So the first thing we're going to do is find the delta H. Okay, so here we have water flowing at 1 meter per second at a height of 0 meters at 10 degrees C will be heated to 25 degrees C. Okay, and the enthalpy values for water at 10 and 25 degrees are 42 kilojoules and 105 kilojoules per kilogram respectively. So now, determine an equivalent change in velocity and an equivalent change in height to increase the enthalpy of the water by 63 kilojoules per kilogram. So this is what we're trying to see, is we're only going to increase it 15 degrees, okay, from cool to lukewarm. We're going to have a 15-degree change. And so that results in an enthalpy change of 63 kilojoules per kilogram. Now let's do calculate the equivalent. This is going to be the change in velocity. Okay, so we have the kinetic energy is calculated by U2 squared minus U1 squared. Okay, and so U1 is 1. Okay, so now let's take, if we start with it at this velocity, what would be the final velocity, okay, to get 63 kilojoules per kilogram? Okay, and we can do this calculation. All right, so we have to first I converted this to joules per kilogram, and then we solve and we find that U2 is 355 meters per second. Okay, so that's really fast. Okay, it's almost supersonic. And if we do the same calculation for the potential energy change, okay, here, this one we don't have to multiply by 2 because this one it's divided by 2 here, so you have to multiply by 2. but this one we don't multiply by 2, but we can just convert it to joules. And we find that the height is 6,429 meters. How high is that? Have you ever climbed that high? That's very high. So as you see, you have to have this significant change of either velocity or height that would be equivalent to a very small temperature change, which is why we normally neglect the temperature changes in our calculations. So where do we find values of enthalpy? All right, we cannot measure enthalpy. I mean, there's not an enthalpy probe. But we can calculate an enthalpy difference if we have heat capacity data. We can look it up on a table. All right, and we can calculate it from the heat capacity data if we know some reference state value. So those are the ways that we are going to get enthalpy, and we're going to learn that in the next part of the course. So here's your calculation for the video quiz. 1 meter cubed of liquid water at 10 degrees Celsius is placed in an incubator at 37 degrees Celsius, where it is stirred with a 3 horsepower motor. In 10 minutes, the temperature of the water has reached 37 degrees. Okay, so you have a work here, you have a shaft work, so you can determine that. All you're going to do is convert the 3 horsepowers to joules per kilogram. You're going to calculate the enthalpy change of the water, and then you're going to find out how much of the heat was added to the water from the incubator, as in just heat crossing the system boundary. So we have a Q, okay? We have a Q, we have a W, and we have a delta U, and for liquids, delta U is approximately delta H. So that's how you're going to do that, okay?